Coloring critical points, a MathByte from iCERM. I'm Professor Thomas Banchoff. I've been teaching at Brown University for 47 years, and I've been associated with iCERM since its beginning several years ago. iCERM, of course, is the Institute for Computational and Experimental Research in Mathematics. The example that we're going to discuss today is coloring critical points, a property that is one of the exercises in visualization that takes place in almost every course, both in secondary school and in college. Ultimately, we want to use calculus to study critical points, but the beginning questions about critical points already take place in algebra, first and second year secondary school algebra. We'll use those examples and then later on show how to generalize them not only to use calculus, but to use calculus not of one variable, but several variables. Let's start, though, with one variable and try to maximize an expression. The expression is 2x minus x squared. Maximizing it means plugging in different values of x and trying to find the highest number you can get. If you plug in 0, for example, you'll get 2 times 0 minus 0 squared, or 0. But if you plug in 2, you get 2 times 2 minus 2 squared, which is again 0. So for two different values, you get 0. What about trying something in between? If you plug in 1, you get 2 times 1 minus 1 squared. That's 1. That's a positive number. It's bigger than either of the things we had before. Doesn't give us too much information, but it gives us at least a conjecture. We have 3 values. The highest one is 1. We might have a conjecture that the maximum value of 2x minus x squared is 1. We could analyze this further using properties of algebra, but at this point, it's really nice to take a look at a graph. One of the most important techniques in algebra, geometry, or calculus is graphing an expression by going to a computer and ask it to plot a certain number of points. And as we take the expression, negative x squared plus 2x, and plot in 20 different points, we get a familiar picture, a parabola. The computer will draw this for us, and in fact, we could put in many more points to make it even smoother. But the computer gives us something more. It gives us a visualization tool that enables us to study not just this, but entire families of functions. The visualization tool is to take 2 successive points on this graph and figure out whether the line joining them is pointing upward, that is to say, toward the right, or pointing downward as we go to the right. So here, it's pointing upward until we get to the maximum point, after which it descends all the way down. At the maximum point, we have a critical point where the curve really changes its nature. And this is really what we want to study. Now, of course, the coloration, as I said, is done by a very simple algorithm. Here we're only using 6 points, and it's very clear that these 2 points here lead to a segment that has a slope that points positively, and here the slope is negative. Again, by adding more points, instead of 6 points, we can go up to 20 points, or for that matter, we could go up to 100 points, and we get something which is indistinguishable, from our point of view, of a completely smooth curve. But the algorithm still is taking 2 close-by points and just determining whether the line joining them has a positive slope or a negative slope. To maximize the expression 2x minus x squared, we can use our conjecture and write it as 2x minus x squared is less than or equal to 1. Whenever we work with an expression of this sort, it's best to get all terms on the same side of the equation. So this is identical to 0 being less than or equal to x squared minus 2x plus 1, simply by moving the material on the left-hand side to the right-hand side. That expression, we recognize, is a perfect square. And we're done. A square of any number is always greater than or equal to 0. So retracing our steps, we can find ourselves back at the proof of the expression that we have found the maximum value of this entire this entire algebraic expression. The visual clues gave us an idea of how to come up with a conjecture. Once we have that conjecture, we're able to proceed and find a proof for it. This is a kind of experimental paradigm, the experimental method that we use in order to come up with conjectures and to find out what the answers really will be by giving an argument that that everyone will accept. The expression we looked before was a very simple expression, but we can look at more complicated expressions, and one parameter families of more complicated expressions. We want to try a different function here, which is a little bit more complicated, because even though cubic equations are somewhat familiar, it's not necessarily true that people have very much expressions with quartic equations. The quartic equation here is negative x to the fourth. Negative x to the fourth is not much different from negative x squared, in the sense that for negative values of x, it's quite negative, and for positive values of x, it's quite negative. The maximum value is 0 at this point. That's pretty clear. And now, instead of adding a multiple of x to the expression, we're going to add a multiple of x squared. In fact, 2 times x squared. 2 times t squared here. And that gives us something which indeed is a little bit more interesting. It's symmetrical again, because all the powers are even powers, so once we know what happens on one side, we know what happens on the other side. Again, our color coding is telling us where it's increasing, and it reaches a point where it decreases, comes back up, reaches the maximum, local maximum again, at least that's the conjectured local maximum. These two things will be the same by symmetry, after which it decreases. So we might plug in this collection of points, or we might just use visual interpretation here, or a visual experiment, and again indicates that the maximum value apparently is at 1, the number that we see here up on the screen. And we can prove that by going back to our algebraic expression. The same kind of algebra enables us to find a maximum for 2x squared minus x to the fourth. 2x squared minus x to the fourth, again, is our conjectured maximum is 1. We do the same thing we did over on the other side and bring it here to the right-hand side of the equation, and then recognize, perhaps with a little bit more cleverness, that the same kind of factorization we got here enables us to factorize and get 0 less than or equal to an expression which is the square of a real number, x squared minus 1 squared. Again, we're done, because x squared minus 1 squared, the square of anything, is a positive number, so our conjecture has been established beyond any doubt whatsoever. We get actually additional information. The additional information tells us that when this expression equals 1, then these inequalities would actually be equalities. You would have it's equal to 1 when 0 equals x squared minus 1 squared. The only time something squared equals 0 is if the expression itself is 0. X squared equals 1, x squared is equal to plus 1 or minus 1. And those were exactly the points we saw when we worked with the expression here. That is to say, x equals 1 gives us a maximum, local maximum. X equals minus 1 also gives us a local maximum. This technique is extremely valuable for studying any function you want. Any function whatsoever can be typed in, and indeed we can have one-parameter families of these functions where we can change a parameter, change a slope to try to figure out what happens. That happens very nicely when we add a times x to this expression, or a times t, sorry. And now as we change this, what we can do is go from the current value down to a value where we have lost the second critical point entirely. This one-parameter family of functions will go down to the point where we have one maximum, global maximum. We still have a local maximum here and a local minimum here. But going down further enables us to completely lose those two critical points. The two critical points have come together, and a local maximum and a local minimum have annihilated each other. When critical points change in form, they generally change in pairs. And indeed, that's a way for mathematicians to try to figure out exactly why it is that certain behavior will change the number of critical points. Studying critical point behavior in functions of one variable then leads us to a more interesting question, which is to imagine working with functions of several variables. We have seen how the computer can help us graph expressions of one variable, x, and find out by visual experimentation where the maximum and minimum values, local maxima and local minimum values, occur. In calculus, we not only study functions of one variable, we study functions of more than one variable. Given an algebraic expression, like negative x to the fourth plus 2x squared minus y squared, the machine will actually give us a picture of the graph by choosing for any point in the xy plane the value x, y, z, where z represents the value of the function, the height of this algebraic expression at this point. We can rotate around to get a nice view of this surface in three-dimensional space. Although it's quite easy to graph functions of one variable by standard techniques, it's much harder to draw a picture or make a model of this object. But we can study it by looking at slices. And the slices really are obtained by putting in a particular value of x. And as you put in a particular value of x, what we have is a constant minus y squared. So the graph itself looks like a parabola. And of course, that's exactly what we get, a parabola. Now we can color to see how that parabola changes. And the changes, as we move across, give us a family of parabolas. And we can see that each of those parabolas is colored red when it's increasing and gray when it's decreasing, exactly the same as what we did in our first study of the parabolas. But we can go the other way and slice in a different direction, slicing by letting y be fixed. And each time y is fixed, what we get is our familiar expression, minus x to the fourth plus 2x squared minus a constant. So it will just be the same object we've seen before moving up and down. And we can get that by coloring that by blue. As we color by blue, we see as we move from this side here, it's increasing, then decreasing, then increasing, then decreasing, starting in the opposite direction. So again, each slice of this is colored just the way we colored things previously in one variable calculus. So we're combining all our experience of one variable calculus together to study an object here, which is a graph that itself can be rotated and looked at in different ways. And as we rotate it, we can move it so that we can take a look straight down at one of the variables. If we look straight down on this, we observe that we are, especially if we change the number of subdivisions here to make it more like our previous graph, we see that we do have the previous graph, which had its maximum value at 1, and it still has its maximum value at 1, because we're subtracting y squared. We can go back and look at the algebra. The algebra was asking us to maximize this particular expression of two variables, minus x to the fourth plus 2x squared minus y squared. And we can use the same algebra that we did before. The expression 2x squared minus x to the fourth minus y squared we think is less than 1. We've seen it on our visual examination. And by putting everything on the right-hand side, we see we have two separate things to deal with, a function of x, which we already know how to factor, and we still have plus y squared. But because x squared minus 1 squared is greater than or equal to 0, and y squared is greater than or equal to 0, the sum of them certainly is also greater than or equal to 0. So we've actually succeeded in using an algebraic proof from secondary school mathematics to give a proof of a fact about functions of two variables, the maximum value, because we not only know that the maximum value is 1, but we even know where it occurs. It occurs when both of these expressions are at their lowest value, when y is 0, and when x is equal to plus 1 or minus 1. So in our graph, which we can call Twin Peaks, the algebraic expression we've just seen shows us, without any doubt, that the maximum value occurs when x is 1 and y is 0, and where x is minus 1 and y is 0. And we can rotate that around and see that indeed our graph does have the behavior we expected. We've been able to solve a problem in multivariable calculus without using calculus, simply using the material we were able to get from elementary algebra for functions of one variable and putting it together as a prelude or a promise of an entirely new realm which is made possible by computers to do the visual exploration, the visual experimentation that enables us to put computation and experimentation together to study the critical point behavior of functions of one and more variables.